Hello and welcome back. So today we're going to continue our discussion of differential equations, and we're going to be talking about growth and decay. And we'll be using exponential functions to model growth and decay in some applied problems. So this is going to be really word problem heavy, but that's really useful. So you'll see exactly how differential equations can be used in a practical sense. So we actually have a model for exponential change. It's y equals ce to the kt, where k is the constant of proportionality. So I should probably say that. So c is the constant, just not the variable. I keep saying that, but that's not what I mean. Just the constant, like the number, the initial amount. So initial amount is what I should say. Okay, and k is the constant of proportionality. It's not well written. T is time, and E is of course just the value of E, and Y is our final amount. Y is our final amount. And we want to prove that dy dt is equal to ky supports that model. All right, so we have dy over dt is equal to ky. All right, so we can rewrite this as dy over k is equal to, or no, not over k, over y. Over y is equal to k dt. And if I integrate both sides, I get the natural log of y is equal to kt plus c, right? And then if I e both sides, I don't really know how to say that as a verb, but I'm going to get y is equal to e to the kt plus c. Now, this can be written as y equals e to the kt times e to the c. E to the c is still just a constant, so I can rewrite this finally as y equals ce to the kt. Right? We can see that that's our model there. So this actually does support the model. So now we can use this information to apply to different problems. So we are asked, the rate of change is proportional to y. When t equals 0, y equals 3, and when t equals 2, y equals 6. What is the value of y when t equals 3? All right, so we know that our initial here, this is our initial, t equals 0, y equals 3. And so we can say that y equals ce to the kt, okay? So when y is equal to 3, we have ce to the t is 0, so we're going to have 0k, right? Anything to the 0 power is equal to 1, so we have 3 is equal to c. Great, perfect. So now we can actually rewrite our model as y equals 3 e to the kt, okay? So that's a k. So we've got our constant c, but we still need to find our k, and we can do that using this information here. So 6 is equal to 3 e to the 2k, right? 6 divided by 3, we're going to have 2 equals e to the 2k. And if I ln both sides, I'm going to get the natural log of 2 is equal to 2k. So then k is going to be equal to the natural log of 2 over 2. So now I can write my actual final model I just want to point out that this is equal to 1/2 ln of 2, which is equal to the ln of radical 2. Hopefully you can see that all those equal the same thing. All right, so these are all k. So now the value of y when t equals 3. Well, our model here is going to be y equals 3 e to the, I can write this as ln of radical 2t, okay? And you could use any of these versions of k, but I just felt like this one would be the simplest. So we want to find the value of y when t equals 3. So y is going to be equal to 3 e to the ln of radical 2 times 3, okay? So actually I would put this in a calculator because honestly at this point in time it's too much to calculate. So we're going to have 3 times the natural log, 3 times e to the 3 times natural log of radical 2. This is quite the equation. And we get y is about 8.485. Notice that I use 3 decimal places to graph, and that's it. That's our answer. There it is. That's our answer. Good? Okay, so let's do another example here. The number of bacteria in a culture is growing at a rate of 3,000 e to the 2t over 5 per unit of time t. At t equals 0, the number of bacteria present was 7,500. We want to find the number present at t equals 5. Okay, so the number of bacteria growing, it's at this rate per unit of time. So that means that dB, I'm going to call B as my bacteria, over dt, because it's per a unit of time, is equal to 3,000 e to the 2t over 5. Okay, so dB is equal to 3,000 e to the 2t over 5 dt. I'm going to integrate both sides, so I get B equals. Now, in this case, U is going to equal 2t over 5, so du is equal to 2/5 dt. So 5 halves du is equal to dt, right? That's our u substitution there. So we're going to end up having 3,000 times 5 halves times, you know, this can just become the integral of e to the u, which is just going to be e to the u plus c, right? Plus c. So 3,000 times 5 halves is equal to 7,500. So B is equal to 7,500 e to the, and I'm going to substitute back in 2t over 5 plus c. Okay? So now we can find here at t equals 0, the number is 7,500. So when this is equal to 0, oops, no, I'm sorry, when t equals 0, not when b equals 0. So b is equal to 7,500, this should be b of 0, e to the 0 plus c equals, dang it, one second, I gotta pause this for a minute. Okay, sorry, I'm kind of making a mess of this, but basically b is in this equation right here is in the form, is it in the form? B equals CE to the KT, right? So B is equal to 7,500 E to the 2T over 5. So when T is 0, C is equal to 7,500. Put a 5 there. All right. I made a mess of that, but anyway, I think you see the point there. So B of T is going to equal 7,500 E to the 2T over 5. Okay. Now we want to find the number present when T is equal to 5. So B of 5 is equal to 7,500 E. If I have 5 here, it's just going to be E squared, right? And that's about, back to our calculator, 7,500 times E squared, oops, E squared equals 55,417.920. So that's about 55,418 bacteria. Okay? Yay, bacteria. They're growing. Okay. Let's talk about growth and decay in terms of the economy. Okay, so a slow economy caused a company's annual revenues to drop from $530,000 in 2008 to $386,000 in 2010. If the revenue is following an exponential pattern of decline, what's the model expected in 2013? Okay, so our model that we're using is y equals CE to the KT. We've been using that this whole time. And we know that in 2008, which we're going to call 0, our number was 530,000, right? And in 2010, which we're going to call 2, because we're starting there, we have 386,000. Okay, so if we substitute in here 530,000 equals C e to the 0 power is just going to be 1. So C is going to be equal to 530,000. So our model is y equals 530,000 e to the kt. Okay. So now we can actually use this information to solve for k. So 386,000 equals 530,000 e to the 2k. 386 divided by 530. Oops. I'm going to put that as a fraction. Ooh, 193 over 265. Is that right? I think it is. Okay. 193 over 265 is equal to e to the 2k. So this is ugly, but the natural log of 193 over 265 is equal to 2k. So 1/2 ln of 193 over 265 is equal to k. Great. This is complicated, but hey, this is real life. So our real final model is y equals 530,000 e to the 1/2 ln of 193 over 265 t. Quite a mess. Okay, so if it's expected to follow a decline, what is it in 2013? Well, in 2013 from 2008 is going to be 5, so we're going to have y of 5 is equal to this, 530,000 e to the 1/2 ln of 193 over 265 times 5. And I'm going to pause while I put this in the calculator because it's boring to watch me do that. Okay, I typed it in. I got my answer. So y is about $239,913.37. I don't know why I got a slightly different answer, but anyway, that's the expected revenue. Expected revenue in 2013. Okay, I do have, I think, 3 more examples, but I'm going to stop the video here so that you can kind of break this up into chunks, all right? Stopping for now.